Embark on a journey of inspiration and discovery with the Purdue Lecture Hall series, proudly presented by the Purdue Institute of Inflammation, Immunology, and Infectious Disease. Join us as we delve into the remarkable odysseys of these aspiring scientists, each crafting their own narrative in the world of science and groundbreaking research. Take a glimpse into their diverse cultural backgrounds and the journeys that brought them to Purdue University. Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel. Welcome, everybody. My name is Tommy Soares. I'm the Director of Scientific Strategy and Relations for the Purdue Institute of Inflammation, Immunology, and Infectious Disease. And today on the Purdue Lecture Hall series, I have the pleasure of welcoming Kaif Khan, who's a PhD candidate in the Department of Chemistry here at Purdue University. Kaif is from Dhaka, Bangladesh originally. He completed his BS honors in chemistry in 2014 and an MS in organic chemistry in 2016 from the University of Dhaka. He then joined the School of Life Sciences at the Independent University in Bangladesh as an adjunct lecturer in 2016 and helped develop the synthetic chemistry lab at the Red Green Research Center. In 2018, he joined the chemistry department at Purdue University and joined Professor Lipton's lab, Mark Lipton's lab in the Department of Chemistry, where he worked on discovering novel compounds for nosocomial infections and developed a synthetic method for C-terminally modified peptides. While doing his teaching assistantship at Purdue, he received the William F. Epple Teaching Award. So congratulations with that, Kaif, and welcome to the program. Thank you so much for joining us today. It's a pleasure having you on.
Well, thank you for inviting me to give a talk.
Absolutely. And with research that is so exciting, and I can imagine just the journey that you took to get here. And hopefully you can take us back and give us a little glimpse of what that was like and what was your introduction into science and what motivated you to get into this whole world of research and chemistry. I can't wait. So
Yeah.
I'm going to let you take the spotlight.
Okay.
You can go ahead, share your screen. I'm going to
Okay.
turn myself off and mute myself. And yeah, we'll go.
Okay. Thank you once again for inviting me to the talk. I'm very excited to be invited. My research is about developing a photo-label backbone amide linker for the synthesis of C-terminally modified peptides. And the second part of my talk will be on the discovery of novel antimicrobials. So First, I'll start talking about where I am from. So I'm from Dhaka, Bangladesh. Bangladesh is a small country that is surrounded by India on three sides. And on a southern border, we share a border with Myanmar. And most of the southern part is also just the Bay of Bengal. So I grew up in the city, which is Dhaka. And here is our flag, which is green and red. The green symbolizes the green fields in the country, and the red color is for all the lives that we have lost in the liberation war. So Bangladesh has a lot of history. We went to war with Pakistan twice, one of which was mainly because we wanted to have our mother language Bengali and they wanted it Urdu. So in around 1952, there was a protest between the students of the University of Dhaka and the Dhaka Medical College, where a few lives were lost. And to commemorate them, this monument was built for them to signify the lives that we had lost. And then again in 1971, we had a liberation war where we became independent from Pakistan. So another monument was built called Smriti Shodha, and it's in the outskirts of Dhaka. There are other nice tourist places in the city itself. So this is one of them, which is called the Lal Bagh Fort, which translates to a red garden. Um, Back before the British took over India, Pakistan, and Bangladesh, the Mughal Empire dominated India, and they had built a fort in Dhaka, the old part of Dhaka, and they stayed in this fort for a while. And then we have another place called Asan Manjil, which is a property that was owned by a very well-known aristocrat who was a politician in Bangladesh back in the early 20th century. So this is another nice spot now. It's now a museum and there's a library in there too. And finally, we have our national parliament where a lot of meetings between the politicians are held. So that's one. And other than that, Bangladesh also has other very nice tourist spots, one of which is the Sundarban, which is one of the largest mangrove forests in the world. And you can see lots of deers and the Royal Bengal tiger there. It's situated on the southern part of Bangladesh. We also have one of the longest beaches, sea beaches in the world. So when I was in Bangladesh, I would go there often, and because I love the sea very much. So this is a very nice place also. Then on the north, we have tea gardens, and a lot of the tea production goes on there. So we are also known for our tea. And there's a lake which is very recently become very famous. It's surrounded by mountains, and people now go visit there. It's really pretty. People who love nature like going there at least once. So with that, I'll go into my education. I went to a school called Sunnydale. This was the campus when I was there. It's this school where I was very interested in science. Our school program had both science and maths very early on. From grade 5, we had 3 different math courses, arithmetic, algebra, and geometry. And then from grade 6 onwards, we had 3 different sciences, chemistry, physics, and biology. And between grade 7 and grade 9, I found two very important role models, I call them. And they were both from the chemistry department. And it's this place where I actually fell in love with chemistry. Then when I finished high school in 2009, I joined the University of Dhaka. Our application process for undergrad is a little tough there. We have to give an exam, and based on our score and our grades in high school, they create a merit list. And when I gave the exam, about 30,000 students took the exam, and of those 30,000 students, I held the merit position of around 840, and I was given the choice between physics, chemistry, maths, pharmacy, so I chose chemistry. So this is our department there. This is a very old building where they currently have teaching labs and administration. And I would say that the research that I'm now interested in, I only was interested in it because of a faculty I met at the University of Dhaka who got me introduced to, or inspired me into getting synthetic organic chemistry. So it is kind of because of him is why I chose this area of research. So in our final year of undergrad, if you have your GPA above a certain threshold, they would let you do research. So I joined a synthetic chemistry lab where they applied synthetic methodologies to develop drugs. So in my fourth year or final year of undergrad, I worked on this reaction, which is known as Bignelli reaction. It is a multi-component reaction where you use this reactant called ethyl acetoacetate, which is a sweet-smelling liquid. It's a flavoring in food. You react it with thiourea and substituted aldehydes. And my role was to do this reaction under solvent-free conditions using nickel nitrate as a catalyst. And we made this inhibitor called 3,4-dihydrothiopyrimidinones. These are used as calcium channel blockers or antihypertensive reagents. And then when I started my master's in the same lab, I was given another project where I worked on making thiazolidiones using chloroacetic acid and metatollyl thiourea, and use the thiazolidinedione and react it with substituted aldehydes using morpholine as the base and ethanol to get glitazone, which are known for being anti-diabetic drugs. One of the limitations of the glitazones are they have cardiotoxic effect. So people who use it for treatment of diabetes develop heart disease later on because of this. So one of the motivations for this project was to design and synthesize inhibitors that could potentially avoid having cardiotoxic effects. So after that, like Dr. Source said, after finishing my master's, I went to independent university as a adjunct lecturer. I taught chemistry to students in microbiology and biochemistry, general chemistry there. So I spent 2 years there and then came to Purdue in 2018. And the reason why I chose Purdue was when I was looking into grad school, I was mainly looking at schools where I have multiple research interests. And Purdue was one of the top in my list because there were a lot of professors who were doing synthetic projects at the time. And I wanted to get into medicinal chemistry related research. So that's why when Purdue offered, I couldn't wait. I just accepted the offer and came here in August 2018. So after I came to Purdue, I joined the Lipton group. We do two types of projects here. One of them is a medicinal chemistry project, and the other is developing synthetic methodology for peptides. For medicinal chemistry projects, we have two enzymes that we target, one of which is the HIV protease, and the other one is discovering new antimicrobials. So this is one of the projects that I will be talking on. And for peptide synthetic methodology, I worked on this other project called a photolabile backbone amide linker. And this is the project I will start talking about now. So amino acids have this general structure where they have this N-terminus, and it's called the amine functional group. And they also have this C-terminus, which is called the carboxylic acid functional group attached to the same carbon. And that depending on what substituents you have on this alpha carbon, you have different amino acids. So our body needs these 20 different amino acids to function. Normally, your body would synthesize amino acids in cells from the N to C terminus, but our methodology in lab, when you're doing these reactions in lab or in solution, how you would go for it is you have your amino acid, you have one of the two terminus protected and the other free because you do not want to have side reactions. So for this case, we have a C terminus that's available. We couple it with another amino acid that has the N terminus free and the C terminus protected. We couple them together and you get your first peptide. Then you check it by different conditions and see if this compound is pure or not. If it's pure, great, you move on to the next step. But if it's not pure, then you'll have to purify it first before you move on to the next step. But the next step is usually taking off one of these protecting groups. So in this case, we're going to take off an amine, and then again, you'll have to purify it. And then once you have your free amine group, you can couple it with another amino acid, and then you get your dipeptide. And then this process goes on, and you end up usually doing a purification step for each of these. And it's usually time consuming and use a lot of resources. So that gets really hard. So a new methodology was developed in the late 1960s, and the person who developed it, Merrifield, got a Nobel Prize for it, and it's called the solid phase peptide synthesis. So in solid phase peptide synthesis, what you do is you you have this resin, which is usually made of polystyrene, and it has some reactive group that you will attach to your first amino acid. So they usually come protected, and you have to do a deprotection. You do this reaction in a vial that has a separation, which is called a frit. So when you wash them, you're just basically doing washes with different solvents and washing it, and all the impurities will go away. You will just have your resin on the frit. Then you use your amino acid, which gets activated, and then you do your coupling step. Once you have finished your coupling step, you have to wash it. You don't have to purify it by other methods. You just wash it with 3 different solvents. You check it if the reaction is complete or not. If it's complete, you move on to the next step, which is another deprotection. And then you wash it until you keep on building your amino acid chain until you reach a point where you want to cleave it off the resin. So for activation, we normally use carboxylic acid. We activate it with what we call coupling reagents, and it generates a very reactive intermediate and 2 other byproducts, which gets washed away in the washing procedure. And then for deprotection, we use a new protecting group called FMOC, which is usually sensitive to base. So we're using piperidine. This base then takes off this FMOC group. It also produces carbon dioxide and this byproduct, which we can wash it away. So as good as this sounds, there are limitations to this procedure, such as you can only build a C-term, like from the C terminus to N terminus. The problem with that is your body usually synthesizes, proteins from the N terminus to C terminus, and usually the C terminus has some sort of modification. So if you want to get a good yield for this reaction on resin, C-terminal modification is not possible. And one of the other limitations is that you have to use strong acids to take your peptide off this resin. So a new approach was developed, which is called the backbone amide linker approach, and this is our project for it. So in a normal backbone amide linker approach, you would have your resin, you would attach it to your backbone amide linker. The backbone amide linker will be anchored to the nitrogen of your first amino acid. So that's your backbone, amino acid backbone. Then you have your N-terminus free, where you can do your peptide elongation. And you have your C-terminus available too to do C-terminal modifications as however you want to do that. So when we wanted to do this project, we wanted to minimize using acids or base, because generally the protecting groups that I have shown thus far are also sometimes acid or base sensitive. And if you take your resin off with it, sometimes you will get multiple byproducts. So we wanted to use photochemical reactions using UV light, and we started identifying linkers by screening some molecules that are known to react with light. So we had these 5 different linkers. Each of these were synthesized with a dipeptide chain, and they were checked under UV light to see how they behave in light. So we noticed that most of these molecules have an absorbance at 300 nanometer, and some of them have absorbance at 350 nanometer as well. So when we tried to do these reactions in the presence of light, we noticed that 5, which is labeled as 7E and 7E here in 2 different wavelengths, they seem to have reacted well in both 300 nanometers and 350 nanometers. All the others had very low yield of product when we tried to do the photochemical reactions. Only 7D had some good activity and some yield at 300 nanometers as well. So we chose 5 as our starting point, but we made some modifications to it. One of which was getting rid of these OME groups. What these do is make this CHO group a little more acidic later on, and we wanted to have that acid stability. So we got rid of these 2 groups, and this is what our design looks like. And each of these functional groups in this molecule has some role in it or another. The first being the carboxylic acid, which we use as the point of attachment to the resin. We have this aldehyde, the CHO group, where we are going to anchor our first amino acid residue. We have this OH group next to the aldehyde because it helps in accelerating the acylation of the second amino acid. And we have this nitro group, which will later be required to do the photocleavage reaction. To synthesize this molecule, we start with this commercially available carboxylic acid with 2 nitro groups and this CH3 group. We do this reaction with this reagent overnight, and we get 72% yield. The product of it looks green in color, but if you crush it, it turns deep red. So that was some interesting light properties we saw in this molecule, and like we were very excited to see this unusual behavior. So we use this material for the next step, which is basically an oxidation reaction between this alkene bond to generate your aldehyde. Another interesting thing came out of this reaction was when we were preparing this material for the next step, we were using DMF or dimethylformamide as the solvent for this reaction. It turned brown first, and then when we tried to transfer it to another round bottom flask with the same solvent, it looked deep blue in color. And then when we added potassium carbonate to this reaction, which serves as a base for this reaction, it turned deep purple. So I like colors, and I was having a lot of fun when we were doing these reactions. So this aldehyde is now ready to do some test reactions. So what we first did was to see if our model did good reactions in solution phase first. So we tried to do this step called reductive amination, which anchors your first amino acid residue to the aldehyde. So we got that in good yields between 51 to 69% yields. Then we tried to anchor our second amino acid. This would be our desired product, but one of the byproducts of this first step of the second reaction is you get both N-acylated and O-acylated product, and we only want the N-acylated product. So in solution phase, normally the reaction was a little difficult for us, so I had to optimize this reaction, and I had to spend a lot of time figuring out how to get rid of the O-acylated product. So the N-acylated product is a little bit more stable than the O-acylated product. And what happened was I was discussing this problem with a friend, and they helped me figure out that I needed something basic enough to react at this CO-O bond and not with the FMOC, because FMOC is also base labile. So reacting it with ammonium acetate gave us our desired product. So after we had tested our model, we reacted it with light, UV light, and got yields of 35 to 54% over 2 steps to generate this dipeptide. So once our model reactions were tested, we tried to apply this in solution phase. And the first step is you have your resin. It had a free NH2 group, and we attached it with a spacer, which is called aminohexanoic acid. So there are 6 carbons between the linker and the resin, and the spacer is to improve reactivity. But when we attached the linker directly to the 6-aminohexanoic acid, we found that it was still cross-linking with the resin. So we had to add another spacer, which was proline, and that helped us avoid this cross-linking or side reaction. So once we had our backbone amide linker attached to the resin part, we tried our first step by anchoring our amino acid by doing the reductive amination reaction in 2 steps to get our first amino acid attached. And then we used our method to add the second amino acid, which gave us both O-acylated and N-acylated product. So when we tried to load the third amino acid, we had to be very careful because if we use piperidine again, the FMOC group will get deprotected. And one of the byproducts of this step after you have a dipeptide, and if you take FMOC, is you generate nearly quantitative amount of diketopiperazine. This is a byproduct that may form and will stop your reaction there, and no other amino acid will be able to couple with it. And the fact that if you have a free OH here, what happens is it helps catalyze this DKP formation. So we had to protect it with a silyl group that had silicon and base in it to stop that from happening. The silicon had some bulky molecules, bulky groups in it that prevented it from giving that as our byproduct. So we moved that further, and we also tried to use a less reactive base to take the FMOC group off and then attach our third amino acid. When we were doing test reactions with the tripeptides, we were able to get between 88 to 100% tripeptide and 0 to 12% diketopiperazine. So after this stage, you just follow the regular synthetic way for making increasing your peptide chain. So using once we have developed this procedure, we used our procedure to make cyclic peptides first, mainly because cyclic peptides are of pharmacological importance. Your body can recognize, your body or enzymes that can hydrolyze peptide bonds recognizes a free N terminus or a C terminus, and a cyclic peptide lacks that. So your body cannot recognize them, and cyclic peptides are generally more metabolically stable in your body. So once we built our peptide chain, we coupled this reaction on resin and made this cyclic peptide, which has 14 amino acid residues, and it is a precursor to a type of inhibitor called sunflower trypsin inhibitor. So we were very happy to get a 90% purity when we did HPLC analysis on it. We also made 2 other cyclic peptides to test our model system, and one of them had 5 amino acid residues and the other had 10 amino acid residues. They were also of some pharmacological importance that we wanted to try out, and they were synthesized with 50% and 95% purity by HPLC respectively. Then we also wanted to try other C-terminally modified peptides. So this one is a thioester, and thioesters are of synthetic importance to build larger peptide chains by a reaction called native chemical ligation. So we built thioesters that had 5 amino acid residues. This project was mostly done with the help of 3 other graduate students who have all graduated from the Lipton lab. And I have not overlapped with them, but I learned a lot from their work. So I wanted to give my thanks to them as well here. 2 sub-projects that came out of this project was we made a new protecting group, and we also built a new UV LED photoreactor. So normally you would protect your acids with the T-butyl group, which is very bulky, and they are usually taken off with acids, and we wanted to avoid that. The other protecting group that is normally used is allyl group, and it's less sterically hindered, but you can also take that off with palladium. So the issue with using just allyl group is that they also end up forming DKP after you have deprotect your FMOC group. So we combined the steric nature of D-butyl and the palladium reactivity of the allyl group and developed dimethyl allyl esters, which both can avoid DKP formation and can be deprotected with palladium sources. So this is just a summary of that we wanted to develop a photolabile backbone amide linker. We developed an ester protecting group that can be cleaved off with palladium instead of acids. Normally, amino acid groups, amines in the group are usually protected with FMOC or something that is either palladium labile or acid labile, or you have to use hydrogenation. So we were able to achieve 4 degrees of orthogonality and applied our system to make cyclic and C-terminally modified peptides. And we call our photoreactor a Mini Cooper. It's a miniature cyclotronic UV photoreactor. We have applied for a patent for it. The idea came to us because the commercially available UV reactors are very bulky and creates a lot of sound. So Miri Niederdrauer, who was a graduate student before I got involved in this project, helped design with the AMI facility in our department to come up with this new photoreactor. So that was the first project that I worked on, and then I moved on to working with making antimicrobials. So antimicrobial resistance is a very urgent global public health threat. It kills almost about 1.27 million people worldwide. In US alone, more than 2.8 million AMR infections occur each year, killing more than 35,000 people. And in the drug business, antibiotics that are available in market or are in the approval pipeline, they are usually either variants of old classes of drugs or have same molecular pathways. So bacteria are very smart. What they do is they develop the same resistance mechanism. So we wanted to look for a different molecular pathway that we could inhibit and killing pathogenic bacteria only. So we chose to go with the mevalonate pathway. Now, mevalonate pathway is a important sequence of reactions that antimicrobials have to develop cell walls. So it is a series of steps that involves acetyl-CoA, which goes on to make mevalonate. But this is the enzyme that we are trying to target is HMG-CoA reductase, and it's the reaction that converts HMG-CoA to mevalonate. Then the mevalonate is used to go another sequence of steps to make this isopentenyl pyrophosphate, which then combines and later forms this undecaprenyl pyrophosphate, which is your main component of your bacterial cell wall. So if you can inhibit HMG-CoA reductase, bacteria don't develop cell wall and they are prone to attacks by white blood cells and can be killed off easily. So the way HMG-CoA works for this reaction is you have arginine, aspartate, lysine, glutamate, and histidine in the active site, which holds on to the HMG-CoA, and then the acidic proton of the lysine, it activates this CO double bond, which gets reduced by NADH into this intermediate called mevaldyl-CoA, and then the histidine helps generate the mevaldehyde and CoA-thiol, which the aldehyde then gets reduced by another NADH to give you your alcohol called the mevalonate. So there are two different classes of HMG reductase. Class 1 is found in humans, and it is involved in synthesizing cholesterol and is also an important target for statin drugs. They have this cis loop in them, which the class 2 HMGR lacks. They have very similar amino acids involved in the active site, but class 2 HMGR is only found in prokaryotes and is a lot smaller and lacks that cis loop. So the Stauffacher lab in the structural biology department had a collaboration with the Southern Research Institute in Birmingham, Alabama, where they screened about 300,000 compounds against this bacteria called E. faecalis enzyme class 2 HMGR. The way they did the screening was by monitoring the reaction of mevalonate to give HMG-CoA, which is the reverse of what usually happens under physical conditions, mainly to monitor the formation of NADPH, which can be measured spectroscopically at 340 nanometer. The reason why this route was chosen was that mevalonate is a lot more stable and available as a substrate. So that's how they screened this many molecules. They had many potential hits, and when they worked with those compounds with their protein, they only found one lead that was very important and is very interesting in a way. It has this salicylic acid moiety and has a sulfonamide moiety here, and also has this long hydrophobic moiety. So it looks a little interesting to us chemists. And when they checked the IC50 values for these under physiological conditions, they saw 50 micromolar inhibition. And when they tried to do it again in the non-physiological condition, which is the reverse reaction from mevalonate to HMG-CoA, the IC50 value was even lower. So they tried to crystallize this inhibitor with the HMG-CoA, and they made a really nice model on it. And then when they overlaid HMG-CoA binding to HMGR and overlaid that with the NBSHA with HMGR, they found out that NBSHA is a competitive inhibitor of HMGR. So at this point, the Lipton lab got involved, and we designed 3 different generations of drug. The first generation was synthesized by Dr. Lopez Perez. She had mainly played around with different functional groups around the benzene rings, and by changing the hydrophobic length of the molecule, and she had found very good IC50 values, but the molecules didn't have that interesting enough cell activity. So when Dr. Hostetler came into the lab, he developed the second generation of drug, and he mainly dealt with making these polar alcoholic groups or carboxylic acid groups, and they were also pretty fine with the IC50 values, but on cells, their activity were not that great. So me and Nia Drower, when she came into the project, we developed a hypothesis that maybe these inhibitors have a secondary mode of action or targeting a different enzyme. So she built these molecules and coupled them with different bioactive molecules, and again saw the similar pattern. So when I joined the lab, we had another hypothesis that we were testing, which is if these molecules are cell permeable or not. So we developed this dimeric inhibitor in 6 steps. You start with this alkyne, and you also make a dimer of it by reacting it with dibromoundecane, which has 12 carbons in between, so that developed that non-hydrophobic moiety. we got rid of these protecting groups called TMS under basic condition, and then we coupled them with the the aniline portion of the molecule, but we had nitro versions of this available. As organic chemists, we memorize and learn about a lot of named reactions. So this step was a named reaction called the Sonogloshira cross-coupling, which uses palladium species, copper, under basic condition. And this was one of the steps that gave me really good yields. Then we converted the nitro groups and the alkynes to alkanes and anilines respectively, and doing hydrogenation reactions using Ren and nickel as a catalyst. And again, we got very good yields with it. Then we tried to attach the salicylic acid moiety with the carboxylic acids protected because we didn't want any side reactions. And finally, we removed these methyl esters to their free acids by using lithium hydroxide. And when I purified this compound and we checked the IC50 value of it, it turned out to be the best activity so far, but we have not tested them on cell permeability yet. Our collaborators who worked on cell had recently changed he moved to a different university, so we are currently looking for collaborators who would do our cell permeability assays. So while we were doing that, we were also coming up with another different approach for these molecules, which was the fragment-based drug design, or this is called fragment to lead discovery. So how you would normally go for these sorts of project is you will have select a fragment library and get them screened. After screening process, you get your hits. After you have found your hits, you want to confirm that they are actual hits, and then you would want to determine how they are binding with the enzyme that you're trying to target. So once you have those data, you try to optimize these fragments and then come up with a lead. And then when you have a lead, you try to alter its chemistry a little bit to find a potential candidate. So the way we went with it was the Purdue Chemical Genomics Facility has this 3 different library of compounds called Cambridge Life Chemicals and Life Chemicals PPI, which stands for protein-protein interactions. The fragments in this group library were very large, so it was not applicable for us, but we screened a total of 7,200 compounds from their library. And we had to come up with certain requirements for them to be compatible with our system. So when you're working with fragment molecules, you want to start with low molecular weight compounds, typically below 300 Dalton. They should have 3 hydrogen bond donors, 3 hydrogen bond acceptors, and they should have a log P value between 0 and 3. So this is called the rule of 3, which is more popularly known as rule of 5 for larger molecules. And it is a requirement that was developed by a scientist named Lipinski. And those requirements were basically so that we can have drugs that are orally bioavailable. And coming back to this p-value it's just the distribution of your inhibitor with octane and octanol and water, which mimics how it would vary between a cell to its aqueous environment. So we did most of our screening with Lipinski's rule of 3. We tried to make sure that we had a diverse group of fragments. By diverse, we mean that they should have a wide range of functional groups so that we could occupy a larger chemical space. And then we again screened them to see if we had similar structures in our library. If we did, we tried to pick the best one or the one that we think would work, have the most activity when we hit them with our enzyme. And we also looked for compounds that are called pan-assay interference compound, or PAINs. These are molecules that have reactive chemical functionalities, and if sometimes you do want them in your molecule, but in our cases, we did not want to have any side reactions, so we tried to avoid those as well. Then we went on to do our initial screening. This was also done in the Purdue Chemical Genomics facility. We had our protein set, so we made a solution of the protein in HMG with HMG-CoA, which is the main reactant of this reaction, and NADP. We tried to hit them with approximately 4,000 fragments, and at the end of this screening process, we found 41 hits. So we tried to again look at these hits and see if if they had very common theme or common structures or not. So we looked for those, and we also looked for some of these fragments had some metabolically unstable groups, so we didn't want those. So we ultimately started working with 36 fragments of those molecules. What we did with them was we wanted to collect some enzyme kinetics data. And so far we have collected 31 fragments enzyme kinetics data. And so far we have seen a wide range of activity in them. We found 3 that are showed very good inhibition. So they are a very good starting points. We have some which have okay-ish inhibition. So we're getting them tested again just to make sure we do not leave out any possibilities. And then we found a few that did not inhibit the molecule as good as we wanted them to do. So after the whole enzyme kinetics data is collected, fragments that showed good enough inhibition will be co-crystallized with our target protein. And once we have those enzymes and fragments co-crystallized, we will check them by X-ray crystallography to see where these fragments bind and come up with new designs for drugs, synthesize them, and get them tested. So if you have, say, for example, 5 possible different hits from it, you can come up with roughly many different interchanging species. And then when you hit them with your target protein, you can find at least some best binders. So currently we are still doing the enzyme kinetics assays, and we are getting ready to do the X-ray crystallography. So that's where this project is at, and I'm very excited to be a part of this process. We are getting a lot of help from our collaborators in the Stauffacher lab, who's mostly doing the kinetic assays and the X-ray crystallography stuff. So we're just waiting to get some data and then come up with new designs for new antimicrobials. Fragment-based drug design is known to have better binding drugs than other ways of identifying drugs. So we are hopeful we will have a solution to this problem. So with that, I want to thank every member of the Lipton lab, especially my research advisor. He's very patient and very supportive and has motivated me and helped me in every possible ways I can think of regarding research and teaching. And I would also like to thank our collaborators, Dr. Stauffacher, the X-ray scientists, Nick, Tim, and Phil, and also the Purdue Chemical Genomics facility. And I would also like to thank Dr. Source for inviting me to give this talk. And thank you all for listening.
Well, thank you so much, Kaif. This has been awesome and such an exciting journey so far, such a exciting way to explain it to us, because I think I'm starting to understand a little bit more as the pieces come together. So great, so great. It must have been a challenge, the transition from Bangladesh to the United States, Was the
Yep.
excitement enough to endure the pains of that transition that you had to go through?
Yeah, I mean, I loved coming to US. I've never been here before.
Yes.
So, I have family in the southern part of the country, but I am the only one in the north in Indiana.
Yes.
The first time I came here, it was my first experience with snow and cold weather. So the fall weather when I came in was cold enough for me to start wearing sweaters, and I thought people were looking at me and looking at me in a very judgy way. Why am I wearing sweaters? So that was a little funny at first. I enjoyed my first 2 years of grad school a lot, and I did not miss home at all. But
Yeah.
then after COVID hit and we were on lockdown, it kind of dialed down a little bit.
Yes.
But coming back from that again, I really like doing research, so
Good.
I had a lot of fun doing research at the Lipton lab.
If somebody wants to get into this world of chemistry, synthetic chemistry, drug discovery,
Yep.
what do you recommend? What types of courses do you recommend that they take?
For undergrads, we offer organic chemistry courses where they learn these functional groups, naming compounds. We are big on that. Then reactions. So I know nurses, pre-meds, chemical engineers, and then majors, they all have to take chemistry courses, and there are specific courses for that. So I would advise anybody who's interested in either synthetic chemistry or drug discovery, that's where they should start, and
Yeah.
then like find a lab to work in.
Yeah, absolutely. And is there how do you find these labs? Is there anywhere that they can start looking for if they're interested in maybe start getting their feet wet in some of these labs?
Yeah, I mean, all research labs here at Purdue, either in the biology department or chemistry department that I've worked with, they have websites of their lab, and these websites have publications and research that they do in the lab nicely, in the website. So you just have to, I would say, first look up a faculty, see if they have a web page. If you see their web page, then you can read about the research that they do. And if it interests you, it usually has their contact information or their administrative assistant information who you can contact. Or you also get the graduate students who work in those lab and have their information as well. So you can reach out to as many people as you want if you're interested in a lab. And that's how you get started.
That's
Like I have
awesome.
it's worth mentioning that I work with one of my undergrads here. She started with no experience in organic chemistry, and now she is amazing. She's taking the course now, but she knows everything already because she has gone through that training process, and I'm really proud of her for that. So
Wonderful, wonderful. And I'm sure you were a great teacher also, because you were a great teacher to us today. I want to thank you
thank you.
so much, Kaif Khan, PhD candidate in the Department of Chemistry, working with Mark Lipton. And what a wonderful journey from Bangladesh all the way to Purdue. Thank you for coming. Thank you for giving us a little bit of a glimpse into your life and into your journey so far.
Yep, and I want to thank you again for inviting me and letting me talk about my research and my journey here at Purdue. So I'm thankful for that.
You're welcome. You're welcome. Anytime. Have a great day, Kaif. Take care.
You too. Bye. Thank
Bye-bye.
you.
Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel.